relative permittivity. Okay, for this relative permittivity, right, sometimes we denote by the letter K or by epsilon R. And the definitions for this relative permittivity, it is actually defined as the ratio of the original field which you are applying to the dielectric to the reduced field or to the net field inside the dielectric. Okay, that means this K is equals to E naught upon E, right? Where E naught, if you remember, it is the applied field, right, across the dielectric, and this E here, it is the net field inside the dielectric which is acting opposite, or I can say which is acting along the directions of the applied electric field. So this is about the relative permittivity, okay, or I can say this as E naught bar upon, instead of E I will write which is the net field inside, so it is actually, you know, the difference between the the applied field and the induced field inside the dielectric. So this becomes the new formula for the relative permittivity. Okay, after this we will see about polarization density, and for this polarization density, right, we denote by the letter P, alright, and this with an arrow on top of this, which means it is a vector quantity. So let us understand what do we mean by polarization density. So this polarization density, it is actually the dipole moment that is developing per unit volume of the dielectric. Okay, so that means if this is my dielectric, okay, which consists of these molecules, and each molecules here are having an electric dipole moment. So the dipole moments of these molecules in a unit volume of this dielectric, that is known as polarization density. So therefore this P is actually dipole moment, okay, upon volume of the dielectric. Okay, so this is the formula for the polarization density. Okay, now I will further explain about this polarization density in this way. Suppose I'm having, this is my dielectric which is in the form of a cube. Okay, suppose it is like this. Now this dielectric, let's say it is having this area, let's say it is capital A, this area also is capital A, and the thickness of this dielectric, let's say it is D. Okay, the surface charge density of this dielectric, let's say on this side, let's say it is minus sigma, and on this side it is plus sigma. So surface charge density of this dielectric, right, on each side it is sigma, and at the same time, let's say the net charge on this side it is minus q, the net charge on this face it is plus q. Alright, so therefore, okay, as you know, the surface charge density, okay, due to the induced charges of this dielectric, we know surface charge density is equals to charge upon area. But in this case, right, this sigma, it becomes sigma p because it is the surface charge density of the induced charges, and the charge, the induced charges on each side, it is plus q or minus q upon, and the area of each side of the dielectric, it is capital A. So what about now, I want to express about this polarization density. So as you know, this polarization density, it is equals to the dipole moment upon the volume of the dielectric. So in this case, we will imagine this dielectric, okay, as a large dipole, as a large dipole. So if you consider this whole dielectric as a large dipole, then the dipole moment of this dielectric, because from the definitions of the dipole moment we say it is equals to the products of either charge times the distance between the two charges. So therefore, if you imagine this whole dielectric as a large dipole moment, as a large dipole I mean, then you will write P is equals to charge on either sides of the dielectric is Q times the distance, it is A, upon volume of the dielectric. What is the volume of the dielectric? The volume of the dielectric is this area times distance. Okay, so this A with this A cancel, so we have P is equals to Q upon D. Alright, so Q is equals to, I think I made a mistake, sorry, this is D actually. So D with D cancel, this A remain uncancelled, so you'll get Q upon A. So look at these two equations. This is your equation 1, this is your equation 2. So from these two equations, right, I can say that this sigma P is equals to charge upon area. Polarization density also is equals to charge upon area. So therefore I can say this sigma P is equals to the polarization density. So please note down this formula. You will be needed this formula in the higher topics.